Okay guys, this is our first video in a module on section 3.2 or over logarithmic functions. And so the very first thing we're going to do is just kind of start by defining what we mean by a logarithmic function and talk a little bit about how we can rewrite it and interpret it. And so I'm going to go ahead and direct everybody's attention to this first white box up here. But our definition of a logarithmic function of base b says for all positive x values where b is also positive, we'll go ahead and make a note here. This is our base. Our base must be some positive number, and our base cannot be equal to 1. If that's the case, then we have this function here, y equals log base b of x is true if and only if x equals b to the y. So some things, first of all, we're going to say that this function right here, y equals log, there's a little subscript b, and the x is technically in parentheses here. This is our f of x here, and the way we would read this is y equals, you know what, actually, I'm going to do everybody a favor here, and we're just going to put this in type text, but we say y equals, maybe, y equals the log base b of x. And so that is how we would read this statement here whenever we see something like this, where b is our base, x is our input, and y is our output there. Now, this being said, what we wanted to do first, or what I want to do first, is take a look at how these two statements are related to one another, because these two statements mean the same thing. So the same thing. So what we're going to do is we're going to talk about a technique for rewriting from logarithmic into what we call exponential form. So rewriting from log form to exponential form. And so this is kind of like our first stop on this journey here. When we talk about logarithmic form, we are talking about the things of this form, y equals log base b of x. But when we have something in logarithmic form, as long as the log is isolated, we could rewrite this into what we call exponential form, which would just be a statement where we have a base to an exponent, and this would be equal to some output here. And so the way I'm going to tell you that we do this is, starting at your base here, you're going to start at your base and draw an arrow from your base across the equal sign over to the other side. And then from that side, we're going to wrap back around and we're going to come over to the argument on our logarithm here. And this is just kind of a really easy way to remember that you always start at your subscript base and hop across the equal sign and back. But if you read this, then exponentially, this means the same thing as the base b raised to the power of y is equal to x. These two things mean the same thing straight up. And so one thing that I want to make sure that we talk about right off the bat is just this. If y is equal to the logarithm base b of x, and y is this thing right here, then one thing we really want to admit is this, and I want to highlight this. Then the logarithm itself is the exponent here. And so when we talk about what is a logarithm, it's a way of asking about what an exponent would have to be in order for a base to be raised to that power and turn into x. Okay? The other thing that I want to acknowledge is just that every logarithmic expression can be rewritten as an exponential expression by using this arrow diagram that you see I've written here. And so what we're going to do is we're just going to take a moment and we're going to look at how we can rewrite logarithmic expressions in exponential form, but also exponential expressions, rewrite them into logarithmic form, because this opens up a lot of doors for us if we can just kind of leap from one form to another. So for example one here, I say rewrite the following into either exponential form or logarithmic form, whichever is appropriate. I notice that letter A here clearly is in what we would refer to as being in this logarithmic form here. So we're going to say that this is log form over here. The right side is exponential form. So because we are already in log form, what we're going to want to do is go to exponential form. The first thing I would recommend you do is just go ahead and set up kind of a template here. And so what we're going to see is that exponential form always makes a statement of the form a base to a power comes out to equal something here. So if we're using our arrow method here, we're starting at the base, we go across the equal sign, and then we come back around to the argument on our log here, the thing we're taking the log of. What this would read as is our base 2 to the fourth power here is equal to 16. And you can clearly see that this statement makes a whole lot of sense in exponential form, but in logarithmic form, it might take you a minute just because Well, we've just kind of started our exploration of logs, and so reading those is going to take some time to get used to. When we look at this next one here and we say, okay, well, if I'm going to rewrite this in exponential form, what's my base, what's my exponent, and what's my output here? One thing that I want to touch on really quickly is this. You notice in the last one, our base was 2 on the log and on the exponential expression. So when we are using this term base b, we truly mean that the base is the same on the log as it would be if we wrote this in exponential form. So our base 10, if we're using our arrow method here, we're going to go from our base or our subscript across the equal sign and back again. We would say that this means the same thing as 10 to the first equals 10. And these two statements would be equivalent here, except for, again, you would be able to probably make a lot more sense of the exponential form of this expression. Now this next one, our base is 3, and we get something really interesting to happen here. We say 3 to the power of 0 equals 1, which is actually an identity, that is a fact. Anything besides 0 that is raised to the power of 0 is always equal to 1. Now you'll notice on these last two expressions here, these are not in exponential form. This one here I'm going to have you change because it should say 5 to the 0 equals 1. That's a typo. But these last two should be in exponential form. What I want to work on is how would I get back into logarithmic form? So first things first, if you're going to go from exponential form back into logarithmic form, the one piece of advice I tend to give people is just go ahead and set up a blank logarithmic expression, and we can start to assess the situation here. The other thing is, it would make it a lot easier for you if you can visualize that these arrows are here, starting at your base, going across the equal sign and back again. So when I say 2 to the third equals 8, that's a mathematical fact, but how would I write this logarithmically? Well, our base would still be 2. And we're reading this as 2 to the third power equals 8. So when I say 2 to the third power equals 8 in logarithmic form, we would say that 3 goes on the right side of the equal sign, and then the 8 is going to go here. And likewise with 5 to the 0 equal to 1, I'm going to go ahead and set myself up with a blank logarithmic sentence here and put my arrows in. But what I would be able to determine is that my base is 5 on both my log and my exponential expression. We say 5 to the 0 power is equal to 1. So now, before we kind of look at just continuing with this idea of rewriting back and forth, one thing that I want to make sure that we really touch on again is just this idea that a logarithm is an exponent. And so in both of these logarithmic expressions here, what you see is that the log is equal to some number, but that number is indicative of the exponent. So when I looked at 2 to the third equals 8, we would say that the 3 part here is what the log is equal to. And so when you look at a log, really what we're trying to answer is, what could I raise the base to the power of to get this argument right here? And that answer is always going to be the exponent that goes on the right side, or the thing that equals the log in the first place. So let's take a look at maybe how I might use this to my advantage if I were evaluating logarithmic expressions for given inputs. So you notice I say insert the given values of x into the logarithmic equation, then rewrite the logarithmic equation as an exponential equation, and lastly tell what the logarithm actually equals here. So in this instance, you're going to notice that I have my dependent variable y equals my log base 4 of my independent variable x, where in this case what I'm saying is I would like to be able to determine what would this be equal to, or what's the value of y when I plug in 16 for x. And so I'm going to make myself a little bit of room down here, but I would say if this were the case and we really were substituting in 16 for my x value, you could see that you might be able to figure this out here. What could I raise 4 to the power of to get 16? Well, it'd have to be 2. But how could I determine this? You know, if you just rewrite this with the 16 in for x, and all we do then is just kind of rewrite this in exponential form, you're going to notice that this question becomes a whole lot easier to think about. So we're asking, what could I take 4 to the power of to get 16 here? Well, the only answer that is reasonable is that y equals 2. And so in this case up here, we're going to say that the whole logarithmic expression would be equal to 2 if x is equal to 16. The other reason why this is pretty important is just because we're going to be graphing a lot of these logarithmic expressions, and it's very good for us to be able to plug in an x value and to get a y value back, as in the case of we plugged 16 into this log base 4 and got an exponent of 2 back. So taking a look at plugging in the remainder of these values here on letter b, if we bring letter b over here, we have y equals log base 2 of our input, which is 64. And so we say, well, what is this the same as? Well, I suppose that if we put in our arrows here, and we're just going to go ahead and rewrite this in exponential form, this would say 2 to the what equals 64. And you would have to just kind of play around with this until you found something that works. So a good one to keep in mind is always 2 to the 5th equals 32. If I do 2 to the power of 5, you see I get 32. If I do 2 to the power of 6, then this is going to give me my 64. So that means that y has to be equal to 6, or in other words, our logarithm has a value of 6 when x is equal to 64. So for our last two expressions here, letter C. Letter C says y equals log base 5 of x, where x equals 1. This is one of my favorite logs to evaluate, the log of 1. And we're going to see why here. As we rewrite this into exponential form, we say, what could I raise 5 to the power of to get 1? The only reasonable answer here is that I must have raised it to the 0 power, because anything to the 0 power besides 0 itself is 1. And then our last one here, y equals log base 3 of 1 over 81. What could I raise 3 to the power of to get 1 over 81? Now, one thing I will bring up here is this, and I'll rewrite this in just a second, but 3 to the power of 4 is equal to 81. So as I rewrite this here and I say, well, 3 to the what equals 1 over 81, you have to keep in mind that 1 over 81 is the same thing as 1 over 3 to the 4th. And so the real question here is, what can I take 3 to the power of to get 1 over 3 to the positive 4? This y here would have to be a negative 4. So we say y equals negative 4. And if that's the case, then I would have to raise 3 not to the 4th, but to the negative 4 to get it to be the reciprocal of 81, which is 1 over 81. Cheers.